That's right, yeah, thank you very much. So this joint work with Domenico Fiorenza, Hisham Sati, with John Huerta, and also with Vincent Schlegel in parts. So, as you may know, even though it's not always evident, this is a conference that is secretly about string theory. And as you may also know, there's a notorious open problem of string theory, namely to figure out what the theory actually is, the full non-perturbative theory. So perturbative string theory is well defined. The non-perturbative theory is open. This was an active problem maybe in the 90s, and then somehow interest vanished. In 2014, at the Strings conference, the annual one, Greg Moore, who's maybe in the other parallel session, kind of reminded the community that we still have no fundamental formulation of M-theory, but physical mathematics must return to this grand issue. I will present some results that I think may be interpreted as being indicative of going in this direction. So I'll start with something very basic, what it might even be the principle of that would-be theory. And I'll start with two very cherished, established principles, the gauge principle and Pauli exclusion. That's essentially all I start with. So the gauge principle in full beauty says, you may never ask if two field configurations are the same. You should always ask, is there a gauge transformation that connects them? Similarly, if you have two such gauge transformations, you should never ask, are they the same? You have to ask, is there a gauge of gauge transformation that connects them? This principle has a beautiful manifestation in mathematics. This is the principle of homotopy theory. It says, you may never ask if two things are the same, two objects. You should ask, is there a homotopy between them? If you have two homotopies, you should never ask, are they the same? You have to ask, is there a higher homotopy, and so forth. So for instance, when physicists model infinitesimal gauge transformations by what they call the BRC complex, this is in a precise sense, that will appear on the next slide, an infinitesimal homotopy n-type for n, the maximal number of n-fold ghosts of ghosts that appear in the BRC complex. Similarly, Pauli exclusion has a beautiful, well-established mathematical incarnation. This is the principle of supergeometry. Pauli exclusion says that no two fermions may ever be in the same state, and mathematically this is the statement that a fermionic field is an odd-graded function on a supermanifold, on a superspace. Now, on the mathematical side, these principles, or these theories of homotopy theory and supergeometry, they have an evident, beautiful unification to what might be called super homotopy theory. By this I mean something that I will not have time to really discuss in these 20 minutes. This is really the theory of what we call the infinity topos of infinity stacks over the side of supermanifolds. This doesn't fit into 20 minutes, but a toy version of this does. It's not a toy version, but a simplified version, in a controlled way, a simplified version, namely the rational version. So recall, to that end, homotopy theory is a very rich, extremely rich theory with loads of aspects to it. There's a plain classical aspect, which everybody knows. This is what you see in the top right corner here, the homotopy theory of spaces, the classical homotopy theory. We've also seen, yesterday at least in Ulrike Tillmann's talk, there's stable homotopy theory concerned with spectra, which are generalizations of the concept of infinite loop spaces. And what should be amplified, because it's very nice and beautiful, is there's a unification of these two aspects to the theory called parametrized spectra. We fix one space, think of it as a parameter space, and over this you have a spectrum that varies over that space, a bundle of spectra. So where plane spectra are coefficients for generalized cohomology theories, we'll see this in action in a moment, these parametrized spectra are coefficients for twisted generalized cohomology theories, which are just the kind of things that we expect to see in string theory, say if we do d-brane charge and twisted K theory. Now it's an old ancient result due to Quillen in '69 and popularized in a simplified way by Sullivan in '77, that if you disregard torsion information, or if you invert all primes, as the topologists would say, the homotopy theory of spaces simplifies drastically and becomes equivalent to the homotopy theory of differential graded commutative algebras. So I'm cutting some corners here. Experts will know that the statement holds only for nilpotent spaces, and I should say co-algebras instead of algebras here. But for the sake of time constraints, and since it's accurate enough, we can think of this as being DGC algebras. Now, since we want to understand what might be super homotopy theory, there's an evident super geometric or super algebraic version of DGC algebras, namely super DGC algebras, where you just, on top of the cohomological grading, you throw in one more Z2 grading with the obvious signs to make it super graded commutative. And the first indication that something might be going on here regarding merging of math and physics is that despite almost complete lack of knowledge for homotopy theory in the ordinary physics literature, it turns out that the cofibrants such super DGC algebras, namely the super Sullivan algebras, are well known in the physics literature under a different name. They're called FDAs, a term that has been maybe introduced by von Neuenhausen and greatly used by Dowry and Frey in a big program that they set up, where they showed that FDAs serve to efficiently construct high-dimensional supergravity theories. In the original article from '82, a very remarkable article, they reconstruct 11-dimensional supergravity in an elegant and beautiful way using a certain focus cycle that they found in the FDA of 11D superspacetime. That focus cycle will appear on its own in just a moment. So similarly, a bit later, it was observed, which is actually maybe a simpler statement, that if you rationalize stable homotopy theory, it's equivalent to the homotopy theory of chain complexes. And since I omitted a co here, I can put a co there, but don't worry about these co's too much. And evidently, there's a super version of cochain complexes where you just have super modules or super vector space in each degree. You can merge these things. This might appear at the very end of the talk if I make it in time. So if you have a space over which a spectrum is parametrized and it's encoded by some DGC algebra, then the rationalization of that spectrum will be, by the left column, the cochain complex, but it's now also sitting over the space, so it will actually be a DG module over that thing. So this is the rational super homotopy theory that we're going to use until the very last slide when I give a lightning outlook on the non-rational theory, which is, of course, what we're really interested in. So one beauty of homotopy theory is that it subsumes cohomology. Cohomology is about mapping spaces in homotopy theory. If you do have a space and map it to some spectrum that is the same thing as a co-cycle on that space with coefficients in the cohomology theory classified by that spectrum. The important point for us here is that for every map, we can ask for its homotopy fiber, and that homotopy fiber is the higher extension that is classified by this co-cycle. You're all familiar with how a two co-cycle, say on a group, classifies the central extension of that group. If one phrases this in homotopy theory, it turns out that central extension is but the homotopy fiber of that two co-cycle. Now, if you have an n co-cycle for n greater than 2, there's no established notion of what the corresponding central extension would be, but you can always form the homotopy fiber, and it does behave just like a higher central extension should be. So that's what we're going to look at. We're going to consider a tower, a whitehead tower of ever higher extensions emanating from something. There's a twisted version of all of this where you map to a parametrized spectrum, then you have an underlying map to the parameter space, that's a twist, and now the co-cycle is a twisted co-cycle. Okay, so we now work out in rational super homotopy theory a tower of extensions, each invariant with respect to automorphisms modulo R symmetries. So beware, everything in the following happens in super rational homotopy theory. At some points I'll identify some spaces that might seem surprising, which does work in rational homotopy theory. Okay, so we start at the very beginning. The most simple, non-trivial object in super homotopy theory is the superpoint, which I call T01. It's the thing that is an ordinary space, it's just zero-dimensional, just the point, but it does have this one odd superdirection. So we can ask, it's easy to see that on the superpoint there's a one-dimensional space of two co-cycles. So we can extend by these two co-cycles. What do we find? Simple computation shows that the result is the super line, or really the super circle if we're doing it properly. The object that underlies the supersymmetry of supersymmetric quantum mechanics, one-dimensional supersymmetry. So this is the thing that is dual to the differential graded commutative algebra that is free on a single generator in degree 1 odd, by degree 1 odd, and closed. So this is a super DGCA, and under duality, under sort of the defining duality that makes DGC algebras models for homotopy types, this is the superpoint. It has one odd coordinate. Right? If you did the same thing in degree even, you would get T1, the rational model for the circle. So to make this more interesting, this is what we're going to do in the following. We will always also double the fermions. So you can just as well consider, of course, the superpoint with n superdirections. Let's just do it for 2 superdirections. Now the first little miracle, I might call it, happens. You compute what are the two co-cycles on this thing. What is the maximal central extension? You find a 3-dimensional space of 2 co-cycles. So the maximal extension will be something that is classically 3-dimensional and has 2 fermionic directions. If you work out what the bracket is, that thing is D equals 3, n equals 1 super Minkowski spacetime. The way this works, this has to do with the relation between supersymmetry and the division algebras. These 3 co-cycles parameterize 2x2 Hermitian matrices with entries in the real numbers, and they just so happen to be the Pauli matrices for real spinors in D equals 3 Lorentzian geometry. So we keep playing this game now. We double the fermions to go to n equals 2 D equals 3 super Minkowski, and we ask what are the invariant co-cycles on this. So on everything, there's now the automorphisms of these group acting, and it turns out if you always take the the semi-simple part of these automorphisms modulo R symmetries, modulo the stuff that just transforms the fermions, one always finds the spin group. So we even this, you see, I didn't put anything Lorentzian here in here. It all, it just comes out. The statement is this comes just out of the extension theory, and we can compute the automorphisms and discover the spin cover of the Lorentz group. So we can double, and there's one invariant cocycle up to scaling. And if you compute the extension, it turns out to be 4D n equals 1 super spacetime. We can double again. Next one finds two invariant cocycles, the two-dimensional space. So we find the 6D theory for n equals 1. Now this has two doublings. There's the type 2b doubling, where you take the same representation, or the type A doubling. The 2A doubling has, it turns out, so all this needs to be computed. This comes out of the math. So this happens to have a four-dimensional space of cocycles. The extension of that turns out to be n equals 1, d equals 10 super Minkowski spacetime. Those who know about this stuff will recognize these dimensions, even though I didn't put this in. These are precisely the dimensions in which Green-Schwarz superstrings exist. But I didn't put that in. It came out. Again, we have doubling. There's famously the 2b doubling and the 2a doubling. Now we find one more cocycle that is invariant under the spin group, and that gives an extension to 11D super spacetime. I'm not claiming that there's no further invariant extensions at this point, but there's no further extensions that do give Lorentzian spacetimes. I'm not sure what to make of these further extensions. Also down here, you can ask what happens if you take the superpoint with three guys. Well, then if you play this game, you get something that is given by 3x3 matrices with entries in the octonions, which is something that has always been conjectured to be related to heterotic M theory, but we don't know yet. So in summary, this is a theorem I proved with John Noetta. There exists a diagram as shown of maximal torus extensions at each stage invariant with respect to the semi-simple part of automorphisms modulo R symmetry. And these automorphisms always happen to be the spin groups. Okay. So next we ask for higher invariant extensions, right? In a process that the homotopy theorists call the Whitehead tower. We exhausted all the two cocycles. Next we ask for the invariant three cocycles. It's an old theorem that in the physics literature is known as the old brain scan, that there is precisely one-dimensional space of extensions here on these 10D super spacetimes, which are called string 2b, string hat, and string 2a. Why do I call them such? Because these cocycles, so I'm writing now as an example, once, remember, all these extensions come from forming homotopy fibers of cocycles. The three cocycle is the WZW term of the Green-Schwarz string. So Green-Schwarz originally wrote down some action functional to make a manifest superstring. It had a complicated term, which they inserted to enforce something called kappa symmetry. And a little later, so it looked complicated. A little later, Eno and Besințescu observed that this complicated-looking term is nothing but the standard WZW term as known from the WZW model of an ordinary group. If you take the target to be the super Poincare group and take this three cocycle, which, I'm not explaining these symbols. These are superfield binds, contracted with gamma matrices. That's the way you find them in the literature. Those who have seen it will recognize it. For others, these 20 minutes are not enough to explain this. It keeps going. Next, we ask for the next higher cocycles. So which extensions are there of the string 2a extension, which is a Derby extension of this spacetime? This is really, if you want to think of this is the total space rationally of the B-field gerb sitting on this space. It turns out it has a whole zoo of higher cocycles corresponding precisely to the type 2a d-branes. I'll say in a moment how it does correspond precisely. Similarly, one finds extensions corresponding precisely to the type 2b branes over this extension. So what do I mean by this? Again, the cocycles to classify these extensions, which now exist in every degree, every even degree here, every odd degree here, they have some expression, which experts will immediately recognize as being the famous WZW terms of this, the super p-Brane models for the super d-branes. So the Green-Schwarz models for the super d-branes. This is the chain-Payton field here, the chunk character really of the chain-Payton bundle, and this is the bifermionic part of the RR forms coupling to the forms. The D0 is special. Just want to mention this. It does happen to sit with the 11D spacetime and the 10D type 2a spacetime in a homotopy fiber product in a pullback diagram, which I think we expand a bit on this in our article, which you can think of being a mathematical incarnation of the Fock-law statement that the zero-brane condensation is what grows the 11th dimension in type 2a spacetime. Now let's concentrate on this 11D spacetime. It itself has higher extensions. One finds a one-dimensional space of extensions, two Derby extensions, which are labeled by M2-Brane. And this happens to have one more higher extension by 6 Gerb, which Should I write the M5-Brane thing? I'll be speaking about this in more detail in a moment, but just to recapitulate what we have so far. So spacetime and M-branes have emerged in some sense from the superpoint as iterated higher invariant extensions. Let's focus on this M-brane sector. And now the strategy will be, we're going to push this down again by mathematical process of cyclification that turns out to be modeling double-dimensional reduction. We push it down again and see what we discover from the M-branes down in lower dimensions. Okay, so first of all, to show again that these terms are justified, so it turns out this extension here, this co-cycle, this invariant co-cycle, is the one that describes the Green-Schwarz M2-brane model, which wasn't written down by Green-Schwarz, but by Bergsoff, Seskin, and Townsend. But actually, the co-cycle itself appears already in Daria-Frey. They just didn't talk about M-branes. They didn't know about them maybe. They were just constructing supergravity, and they use this. They have a process that constructs 11D supergravity as a classical action function from just this thing. Similarly, the M5-brane extension here is classified by 7 co-cycle, so it looks more complicated, but nevertheless, so it exists. This was also already stated in Daria-Frey. They already saw this. You need a quite sophisticated Fierce identities to see that this is a co-cycle, which I think is due to Daria and Frey. Then it seems to have been forgotten. It was rediscovered and understood to be the WW term of the M5-brane by Pasti, Sorokin, and Turin. They don't cite Daria-Frey. It seems they didn't know. What we're going to do now, what we want to do is, you see, we have this funny co-cycle sitting on this extension. What we do want is co-cycles on space-time. I'm going to do an equivalent descent now in homotopy theory down of the M5-brane co-cycle down here, and we will find a single co-cycle in twisted cohomology. It turns out by a general principle of homotopy theory, which we just explained a bit in this article here, what you have to do to make such a descent work is you first of all have to arrange that the coefficients sit in a similar homotopy fiber sequence as the spacetimes do. A little computation shows that this can be achieved, this is solved, this problem is solved by putting the quaternionic Hopf vibration here. So you ask, how can I find a homotopy fiber sequence like so, with something here, which will have an interpretation of being the homotopy quotient of B7Q by B3Q, and it turns out the solution to this is the 4th sphere. The 7th sphere sits over this as an SU2 bundle. This SU2 bundle has a second Chern class, and rationally that's what one sees here. So this is rational. Remember here, so I'm exchanging, you see I'm exchanging an Eilenberg-McLean space by an odd sphere. So this works in rational homotopy theory. And I'm exchanging something more complicated to an even 4th sphere. Second part of the statement is that the co-cycle does descend. There happens to be a map that factors this diagram. This commutes up to homotopy, this commutes up to homotopy. And this is now the descended, by some theorem, this is the descent of this co-cycle. So we have a unified version of the M5, M2 co-cycle, and I can't explain the full computation here, but just to give you a plausibility argument for why this is not going entirely crazy, why this is related to something you have seen before and you know. So what is this S4 coefficient? So the DGC model for it is by a classical result of Sullivan's, or maybe even, I guess that was written down by Sullivan. It's modeled by the DGC algebra that's generated by a guy in degree 4, a generator in degree 7. The guy in degree 4 is closed. The generator in degree 7 has differential proportional to the square of the guy in degree 4. This equation, you see, we interpret this now as coefficients for these co-cycles. So this will be interpreted now as the background charge for the M2-brane, which is the G4 field. And this is the background charge for the M5-brane, which is the G7 field. And this equation, which is really this 4-sphere equation, is of course the equation of motion of the C field and its dual in 11-dimensional supergravity. So this is not the proof of the statement, but this is one way to see quickly how it's plausible. Okay, let's focus on this M-brane co-cycle a bit. Remember, the left-hand side was really the extension of the type 2A spacetime. You see, I'm working us now towards finding the double-dimensional reduction of this. We want to re-express the stuff we found in 11D in terms of structure that we can see in 10D. So we write this explicitly again as the extension of the 10D spacetime that we had. And for symmetry reasons, we do the same thing for the 4th sphere on the right. Now, the 4th sphere is a circle extension of something, namely of the homotopy quotient by some circle action. So a natural solution is that regard the 4th sphere as being the unit sphere in the space that is the reals plus the quaternions, and let S1 act in the canonical way as a subgroup of SU2 on the quaternions and form the homotopy quotient. So this is an orbifold here, since this action is not free, it has 2 fixed points. And then S4 is the homotopy extension of this. Notice that this orbifold that appears here from just our extension business is the orbifold that happens to appear in the neo-horizon geometry if you put a black M5-brane at an A-type singularity. So, in conclusion, our unified M2 M5 co-cycle is really of this form. It goes from an extension of 10D super spacetime to an extension of this orbifold S4 mod S1. And now, let's think a bit more about what we're doing here with our extensions. It turns out, so forming these extensions is a derived functor from super homotopy types equipped with a 2-cocycle, so with a cocycle that classifies circle extensions, which one writes like the slicing notation. This is super homotopy types equipped with a map to BS1, and our extension process, forming homotopy fibers, is this functor here. This turns out to have a derived right adjoint, and the derived right adjoint, one can work out, acts by cyclification. It forms free loop spaces, homotopy quotiented by rigid rotation of loops, which in the string theory literature is often called the twisted loop space. On cohomology, this means takes a space with some cohomology to the corresponding cyclic cohomology. This is a very general statement about base change in infinity topos here. There's also a left adjoint here. And the base change, for those who know, is that induced by the map from the point to BS1. But anyway, so this exists. And so we can make use, whenever we have an adjunction, it means it's telling us something about the inner structure of the things we're considering. So let's apply this. So I apply cyclification to the diagram we had before. So this is now the cyclified M2, M5 brane cocycle. Apply free loops and homotopy quotient out rotations. And since we have an adjunction, and now here's a right adjoint applied to a left adjoint, there's the adjunction units that go from 10D spacetime, so this canonical maps that homotopy theory gives us, and from this orbifold to this thing. The composite that appears here, if you go from here to here, is called the adjunct under our adjunction between the M2 and M5 brane cocycle to this one. You can work out what this is. Turns out that is the cocycle for the unified, F1, D0, D2, D4 and NS5 cocycles down in 10D. So what does this mean? So, to make this plausible, first of all, one works out what is the cyclic space of the force sphere that is sitting here. There's an old formula by Sullivan and some student of his whose name I forget now, back from the 70s, who worked out Sullivan models for these cyclic loop spaces. And it turns out if you apply to the force sphere, you get the DGC algebra that is generated precisely by the Bianchi identities for the field strengths of these branes. You see the NS field strength here, which is closed. You see the beginning of the twisted Durham complex here for the RR charges of these branes up to D4. And you see the more complicated Bianchi identity for the NS5 brane. And then what I'm not showing is one has to compute that this thing, taking coefficients in here, really does assign these Green-Schwarz cocycles for these branes. This gives rise to an evident question. If we want to continue, can we actually complete this diagram? That's a mathematical question. And the physical question is, well, where's the rest of the branes? But recall that physics 4 clause says, no, the D6 and higher is not supposed to rise from double-dimensional reduction of the M5 and M2. It's supposed to rise by some mysterious process of gauge enhancement. So it's okay that we don't see it from this double-dimensional reduction, but the question is still, does it appear somehow? Okay, it does, but let's first make some room. We need to be a bit more sophisticated. So it turns out a direct lift here doesn't exist, but if we linearize the problem in homotopy theory, it does. So if we go to, remember, stable homotopy theory was like homological algebra, which is about linear stuff. If we kind of linearize in this sense, if we take the Goodwilly linearization, in that I take these spaces here, which all sit over S3, and I take the fiber-wise suspension spectra and then the corresponding infinite loop space. So this is making the problem fiber-wise linear. Yeah, just if you haven't seen this, just accept it maybe. So I'm asking now, can I find this linearized lift? Can I solve this obstruction problem sort of in Goodwilly linearization? And there's a curious fact that made this work. In 2000, Roig and Zaralegi, they had a method for computing minimal models for such parametrized spectra in rational homotopy theory. And they compute that in this fiber-wise suspension of S4 over S1, sitting over S3, there sits a copy rationally of twisted connective K theory. The way this works roughly is, this has two fixed points, so this homotopy coefficient, this orbifold looks like an S3 with two copies of BS1 attached to the poles. And as we're forming fiber-wise suspensions, we're forming the suspension spectra of BU1. So there's some rational version of Snaith's theorem going on that picks out a copy of KU there. And now it does work. There is now a lift of the original doubly dimensionally reduced cocycle that factors like so. So the rational version of this twisted K theory is just the twisted Durham complex that you all know. And this way, we find that all the d-brane charges find their home rationally as they should in the twisted Durham cohomology. Okay, I need to come to an end, I suppose. I have 5 minutes left or something. 1 minute? Okay, so we found the double dimensional reduction of the unified M to something to brane. So we want to repeat this process. I'm looking at it as untruncated KU now. So we do the extension process we do the double dimension reduction one more dimension down. We came from 11 to 10, let's go to 9. So we apply this equivalence, we apply cyclification, we pre-compose with our adjunction unit to again produce the adjunct, now producing a cocycle in 9D. This is compactifying the 10D theory on a circle. Now remember that the 9D theory also had another extension, the type 2b extension, which I'm writing here. So we can write that down. And whatever cocycle the type 2b, if we can find a cocycle here on type 2b spacetime, we can doubly dimensionally reduce it by applying cyclification, precomposing with our adjunct unit, forming the adjunct. And if I can now find an equivalence here, such that the cocycle is Lorentz invariant, is an invariant cocycle, then by adjunction I will have defined from the 2a cocycle a 2b cocycle. Turns out this exists. This is this main theorem we have with in this T-duality article. So you have to put K theory plus shifted K theory, then this equivalence exists such that everything is invariant, which is our working the rule of the game, and one finds this cocycle which happens to be precisely the one for the type 2b branes. So this is the incarnation of T-duality on this cocycle level. In fact, one can analyze this in more detail. The commutativity of this diagram, which is now really fast, but let me just claim this. This is equivalent to what's called the Busher rules of RR fields, usually attributed to an article by Kentaro Hori, maybe in the parallel session. We have some quotient here over some thing called the T-duality 2 group. If we forget the K-theory part, we get another commuting diagram, which turns out to be precisely the rational incarnation of what's called topological T-duality, introduced by Bauknecht et al. And made precise by Bunkerumpf and Schick. We can find, coming back to our story of taking any cocycle that we find, we should form the extension. We form the extension that's classified with this total cocycle. It turns out to be the double space-time, in the sense of physicists use it, where these two circle fibers, the type 2a and the type 2b fiber, both appear, and there's a gerb sitting over it, which is this head, which makes it the generalized geometry. We can still pull that back now to 11D, since this is in 7D, to get a 12D thing sitting over 11D spacetime. And that turns out to have all the properties rationally to be a candidate for the rational model for an F-theory fibration. In particular, if you do rational, hence GL2R rotations on this doubled copy here, it corresponds to S-duality on these brane cocycles. So in conclusion, a fair bit of the expected structure of M-theory emerges out of the superpoint in a rational super homotopy theory. Maybe the main impact of this is that it leads to an evident conjecture. You want to say, well, if that is true, then maybe the full theory emerges, since we were just working at this rational toy approximation to the full story. But we know what this full supergeometric homotopy theory is, so maybe we should do the whole thing there. This needs to be worked out, but there's one thing I may end with, as long as nobody kicks me from this stage here. It turns out that if you do go to full supergeometric homotopy theory, there's a precise sense in which the superpoint itself emerges from the empty object, from the initial object, by some sequence of mysterious steps that I can't explain here, but which I explain in this chapter to a book on the foundations of mass that will appear later this year. I thank you for your attention.